Okay, so let's get started. Just a quick check. Is this the last slide we left off with? Can everyone hear me? Okay. So just a quick check. Is this the last slide we left off with, or did we cover this already?
We did not cover this.
We did not cover this? Okay. I'm going to go back one slide. Did we cover these two?
Yes.
We did both?
No. Yes, we did both of them. Yes.
Okay. So we'll start with this one then. This one is also pretty straightforward. This time we're going to do a basic reaction, a basic solution. Okay. So we still need to do our normal steps. So I want you to do all of your normal acidic steps here. And then we're going to go ahead and add in our basic steps. So I'm going to let you do the acidic steps first, and then we will go through it and break down the basic steps. Okay. So go ahead and take this time, work on that. Okay, is anyone having trouble starting this one? All right, so we'll split this up first, okay? I'm going to do the same thing I do normally for acidic steps. So first, I'm going to divide into my half reactions. I have one on the left and one on the right, okay? With that said, let's focus on the left side for now. On the left side, I have one Mn on both sides. I don't need to balance that. The next thing I need to balance is your oxygen. On the right side here, I have two carbons here and one carbon. So I need to put a 2 in front right over here. Okay. That 2 in front will make sure that I have the same number of carbons on both sides. Now, with that said, once I put the 2 there, then I can focus on balancing the oxygens for both sides. How do we balance oxygen? What do we add? You add water. Okay. So in both scenarios here, we go ahead and add water, right? So remember, we added the 2 here to indicate that this now has the same number of carbons on both sides. I add water to both sides, right? This one has water on this side to make sure that I have the same number of oxygens on both sides. I add water to this side to make sure that this also has the same number of oxygens on both sides. Because this tells me that I have a total of 2 oxygens. Oh, sorry, 6 oxygens here. So this tells me that I need to add 2 more on this side. Any questions on that? Okay. With that said, once I've added the oxygens, I need to add in my hydrogens. So how many hydrogens am I adding? Well, let's call this left side and right side, okay? So on the left side, where am I adding the hydrogens? To MnO4 or to MnO2?
MnO4.
To MnO4, okay? So this is the side that's going to receive the hydrogens. How many hydrogens is it going to receive? 4 hydrogens. So it's going to be written as H plus because we're dealing with acidic solutions, okay? And on the right side here, I'm going to add it to the opposite side, not C2H04, but to the side that says CO3. So this one's going to end up having the hydrogens, and we're also going to do 4 hydrogens because this gives me 4 here, and it's going to be H plus on that side. Any questions so far on that? Okay, once I've added in my hydrogens, I need to add in my electrons. So if I look at my overall charge on this side, this is a total of +3. This side is a charge of 0. This right over here is a charge of -2, and this side is a charge of +2. So to make sure I have the correct charge on both sides, I need to make sure I add the electrons to the side that's more positive. positive 3 and 0, this side is more positive, so that's where we're going to add these 3 electrons. And in this scenario here, the positive 2 is more positive, so I'm going to add the 2 electrons here to make sure that this comes out to the same value. Okay? Sorry, this one is actually not positive 2, it's actually 0. Because this has 2 of them. So it gives me a negative 4, positive 4. But the 0 is still more positive than this negative 2. So I still need to add 2 electrons to this side. Okay, any questions up to this step? All right. So with that said, once we've gotten to our half reactions and we've balanced them, we can actually see which one's reduction, which one's oxidation. Reduction is the one that adds in the electron. Oxidation is the one that loses the electron. So this is leaving. And this is going into the equation. Okay, any questions up to this step? Okay. So the next thing you want to do is you want to make sure that both the number of electrons being lost is equal to the number of electrons being gained. So if on the left side I'm gaining 3, but I'm losing 2, something's not right here. So I need to make sure I multiply them with a multiple that will give me the same number of electrons on both sides. So if I go back real quick, the left side here, the entire thing is going to be multiplied by 2. The right side here, the entire thing is going to be multiplied by 3. So that we have new numbers and that both sides have 6 electrons being transferred. Any questions up to this part? Okay. So once we do that, we can go ahead and just cancel out the electrons. They show up on both sides. Makes my life a little easier. I cancel anything that shows up on both sides. So right here, I can see that I have 12 hydrogens, 8 hydrogens. I can cross out this and put a 4 and cross this out. And then here I have water and water. I can cross this out and cross this out and put a 2. So they do the same exact thing here. You can do it right then and there before you go ahead and add it into the bottom. Once you get to this last step, are you done? Yes or no?
No.
No, right? We're dealing with a basic solution, so we need to go ahead and account for the basic solution steps. And also, this is not done no matter what, because you still need to add in your charges. Okay, so if you haven't done so yet, I want you to copy this down, and then we're going to go ahead and start adding our OH to it. Does anyone need time to copy it down?
Yes.
All right. I'll give you a little bit to copy it down first. Okay, so I'm assuming everyone has copied this down now. We're going to go ahead and add in our OH. How many OH do I add and to which side? I add 4 OHs. And since this is an entire equation now, I add it to both sides.
Professor, I just have a quick question.
Sure.
So how will you know exactly when to add OH instead of just straight up H2O?
So once we have finished this, right? When you look at this right here, this is everything you need to do for the acidic steps. Okay? So we're done. Does that make sense?
Yeah, also we're just making it more neutral. We're adding the buffer, right? We're making it more basic.
We're not adding any buffers. We're adding a basic solution. So this is done in a basic solution. You must do the acidic solution first, and then you do the basic solution. Sometimes you don't have the basic solution. Sometimes it says you're given an acidic solution, just solve it in an acidic solution.
Okay.
Our goal is to cancel out the H+. So we're going to add 4 OH minuses. And since this is an entire equation, I must add 4 OH minuses to both sides.
Okay.
And then I'm going to go ahead and change this into water. So this becomes water. And then I can use that to cancel out the waters.
Oh, I see. Okay.
Okay.
Yep. Thank you.
Okay. So with that said, we add it to both sides. This is our equation. It's 4 OH minus, 4 H plus, 4 OH on the left. I change this into water, and then I can cancel out any extra waters on both sides. So this is gone, becomes a 2. So this becomes 2 H2O on the left, on the right side. And now I have a 4 OH minus on the left. Any questions so far? Okay. In most cases, once you get to the final equation, if you look here, if your final equation has H plus in it, then you're dealing with an acidic step or acidic solution. If your final answer has an OH minus in it, you are dealing with a basic solution. Okay, any questions? Now remember, you must include the states of matter that originally came with it. If it is just a solid, write it as a solid. If it was a gas, write it as a gas. Anything that has a charge on it is considered aqueous. Okay, does anyone else need time to copy this before I move forward? Okay. So before we do this one, question for everyone. Do you want to do more practice with basic solutions, or do you want to move forward to the rest of the lesson? Because this does take up a lot of time.
Can we do like one more? One or
Okay,
two?
so we'll do this last one right here, and then we'll move forward, okay? So this one doesn't have any answers written on the, well, no, the PowerPoint. This is one that I created. So we're just gonna work on the screen right here, okay? If you look carefully at this one, it's a little complicated because I have Ag and Cn, I have O2, and then it just makes AgCN2. Now, do you see two different half reactions? Or can you see two different half reactions? You cannot, right? It gets a little complicated. So what you can say is you have Ag plus Cn minus, and this changes into AgCN2, okay? That's on the left side. On the right side, I have O2, it's in the gas form, and it changes into blank. So these are your two half reactions. All right. With that said, let's do the AgCN first. So it looks like I have one Ag and one Ag. It's not an issue. But I do have, if you look carefully, two Cns. So I need to go ahead and put a 2 in front of that Cn. Okay, so now I have one Ag, 2 Cn becomes AgCN2. Any questions up to that step? All right. With that said, do you see any oxygens or hydrogens? No, right? So we can actually skip all of the things with oxygens and hydrogens. Let's focus on just the charge, okay? On the left side, what is my overall charge? -2. What's on the right side? What's my overall charge? Not 0. There was a negative here. So it is a -1. Okay. Where do I add the electron and how many? I add the electron to this side. Okay, 1 on the right side. So let me rewrite my entire equation just so I have it. I'm also going to clear this part out so we can just go ahead and write it here. So I have Ag plus 2Cn minus changes into AgCN2, well, Cn2 minus, plus an electron. Okay, any questions on that so far?
Oh, wait, could you go over that again?
I put a 2 here because I want to make sure both sides have the number of CNs, number of carbons and number of nitrogens, okay? Does that make sense?
Yeah.
'Cause there's a 2 here. That's why there's 2 CNs.
Yeah.
Then I see that the overall charge is -1 for a CN, but I have 2 CNs. So this is overall charge of -2. The overall charge on the right side is -1. So I need to add an electron to this side to make sure that both sides are -2.
Okay, got it.
Okay.
Got it. Yeah.
So that's done. We're down to this. Okay. Let's focus on the right side now. For the right side, what do I need to add to the right side of the equation? And we can ignore the phase for now. I have O2 on the left. What should go on the right? Not just randomly an O. How do I assign oxygen?
Water? No,
Water. I need to put 2 waters here, okay? To indicate the same number of oxygens. Does that make sense? I'm going to take your silence as a yes. Now that I've added 2 hydrogens to that side, what do I need to do to the other side to balance the number of hydrogens? plus 4H plus, okay? I'm adding 4H pluses to the side. Now let's look at the charge. What's my charge on the left and what's my charge on the right? My overall charge on the left, there's 4 of them. So I need, it's a positive 4 here. Okay, charge on the right is 0. So even though this is a positive 1 here, there's 4 of them. So I need to account for each one. This goes back to stoichiometry. So on the left, it is a positive 4, right side is 0. How many electrons do I add and to which side?
4 electrons to the right side,
Not to the right side,
to the left side.
to the left side. Okay. Remember, electrons are negative. So I need, essentially, this cancels out. This becomes 0. All right. So let me go ahead and rewrite that entire thing down here. So we have it. So I have O2, and I'm adding 4 hydrogens, and I'm also adding 4 electrons to this side. On the right side, it is 2H2O. Any questions so far? Okay, with that said, how do I make sure that the number of electrons being transferred or gained is equal to the number of electrons being lost? What do I need to change?
Could you repeat that question?
How do I make sure that this and this are the same number? I multiply this entire equation by 4. Okay? So I'm going to go ahead and rewrite that for you. I use a different color so it's a little easier to see. Okay, so this is my left side, this is my right side. So this is my equation on the left, my equation on the right. Is everyone following along so far? Once again, I'll take your silence as a yes. Okay, so we're going to go ahead and write the final answer back up here, just because I do not have room on the bottom. So I'm going to put them back together. Everything on the left stays on the left. This is our arrow right here. Everything on the right stays on the right. And anything that shows up on both sides gets canceled out. So I can cancel out the electrons now because essentially it's the same on both sides. Okay. Any questions so far up to this step? All right. So I'm going to go ahead and erase everything down here now. Once I have done this, am I done? Have I finished? What else do I need to do now? We need to add OH because we are dealing with a basic solution. Everything we did up to this step was an acidic solution. Okay. So if I look here, there's 4 OH minuses. I need to add, 4 OH minuses to that 4H plus. Okay. If I add that to the left side, I must also add that to the right side. And with that said, this suddenly changes into 4H2O. Okay. And once it becomes 4H2O, I can cancel things out. I can cancel out this entire thing. And this now becomes 2H2O. So using that information, I'm going to rewrite my entire equation now. And then I'm going to go ahead and assign all the phases. Anything that you see that was originally a solid, you keep it as a solid. Anything that has a charge is aqueous. And anything that was water is usually just liquid. And then this one was gas, so we keep it as a gas. This one is aqueous again, and then this one is aqueous. All right, any questions so far? Okay. So let's start moving forward then. The next thing we're going to talk about are electrochemical cells. We have two types we're going to look at: voltaic, also known as galvanic cells, right? And then electrolytic cells. So both of these involve two things: electrical energy and chemical energy. Okay. In our first scenario here, a voltaic cell, also known as a galvanic cell, is a spontaneous reaction. Does anybody remember what spontaneous means?
It doesn't need energy to start.
It does. So that's where you want to clarify. It may need an initial energy to begin, but it doesn't need constant input of energy to continue. So most things do have an activation energy where you have to overcome that first, but the rest of it is smooth sailing. So in other words, it will just require the beginning energy. It doesn't require constant input of energy. It will move forward on its own. Does that make sense?
Yeah.
Okay. For a non-spontaneous reaction means that this reaction will not go in that direction unless you force it. By forcing it means you're putting in energy to make it go in that direction. So a spontaneous reaction, what it does, it actually takes your chemical equations, right, your chemical energy, and it changes into your electrical energy. Okay, so all of your chemical energy, it will change that into electrical energy for you. Because it is a spontaneous reaction, the reaction is happening on its own. In the process of that happening, you are just simply here to extract the electricity that comes out of it, because this reaction is moving forward. An electrolytic cell is the opposite. This reaction will not go forward in this direction that you want. But if you put in electrical energy, you can force this reaction to go in its chemical response. So you can force a chemical reaction by adding in electrical energy. To give you a little mini example of what I'm referring to, think of the first one as if you were in the middle of trying to charge your cell phone. Oh, sorry, using your cell phone. The reaction is happening on its own. It's going forward, and it's using the electricity in the process, okay? The electrolytic cell is the opposite. You are essentially charging your cell phone. You're forcing your cell phone to undergo or reversing a reaction so that you can use that reaction later on. Okay? All right. With that said, there are two types of electrodes that you're going to look at. We have one called the anode and one called the cathode. These always remain true, no matter which one we're looking at, whether we're looking at electrolytic or voltaic cells. Okay? So once again, these always remain true. Anode is where your oxidation occurs. Cathode is where reduction occurs. So you may want to write that down. Okay. Any questions? Okay. So just to give you some examples, this happens to be drawn inside of one solution. Usually this is done in two different separate solutions. So it's two separate containers. Okay. And we'll talk more about that later and we'll see it. So galvanic cell, also known as your voltaic cell, it's a spontaneous reaction that happens on its own. The electrons will move forward and you can actually extract the electricity by simply attaching a light bulb or something that uses that electricity. Electrons are being transferred on its own. That is electricity. Electrons, a movement of electrons is electricity. So we are essentially just extracting that information, using it to our benefit. Okay. With that said, in an electrolytic cell, the reaction will not go forward on its own, will not move in that direction. Because you could put some kind of power source that is stronger than the output energy that they produce, and you can essentially undo the reaction. How many of you have heard of the, I don't exactly know the term, but it's kind of like free energy.
Oh,
Or renewing energy, where like you have an unlimited source of energy, like you can use something to regenerate the energy and vice versa. A lot of people always talk about it when they're trying to talk about science. Not necessarily a windmill, but something similar to that, as if like you're using energy to remake energy. Like they say that they have something that you charge something and then you reuse it and it just regenerates the energy over and over again. Perpetual energy, that kind of situation. Yes. So not a water wheel, not bicycle light, things like that, but perpetual energy. So the truth I can tell you is that it does not exist. Okay. So to give you an example, if I am looking at a battery, if I charge that battery, right, I use a certain amount of energy to charge that battery, and then it expends energy. But over time, things will corrode inside and things will not give you 100% back. So if you charge a battery to 100% and you use it, you're actually not using 100% in the process. Some of it corrodes, some of it gets damaged along the way. That energy is not 100% be stored back into the battery. So that's why rechargeable batteries over time will wear out. Okay. So let's continue. So we're going to talk a little bit about the spontaneous redox reactions. The main one we're going to focus on is your voltaic cells, because we always want to use or find a way to extract energy for our benefit. We don't want to go ahead and have to put in energy when we can go ahead and try to extract the energy. So we're always going to look at the spontaneous reaction, things that will move forward on its own, and we can extract the energy in the process. So we're going to learn more about this later on, but comparing zinc and copper, one of these tends to give electrons more so than the other one. So one tends to give electrons, the other one tends to receive electrons, depending on which electrons you paired, which metals you paired together. So the spontaneous reaction is that one will give electrons, the other one will receive. So zinc is the one that is giving electrons over to copper. And we'll learn more about that later on, but that is a spontaneous reaction. In the reverse reaction, copper will not give electrons to zinc unless you put in energy. In other words, you force this reaction to happen, you can make copper give electrons to zinc, but that requires energy in order to do that. Okay. So now that we know that zinc is the one giving away electrons, it is considered oxidized. Copper here is the one receiving electrons, is being reduced. So in terms of my anode and cathode, this is where my anode is happening. Anode is happening at the, I'm sorry, I wrote that wrong. Anode is happening at the oxidation, and then cathode is happening with the reduction. So reduction is happening inside of the cathode. Okay. All right, any questions before we move forward? Okay, so you won't really see the electrons being transferred if they're all in the same container. So if you put this into one beaker, everything is just there. The electrons are being transferred in there, but you can't see a difference and you can't extract it. You would need to actually make sure that it's separated into two different containers, because then you can see that the electron is moving out from one end on one wire to the other, and then you can find a way to extract that information or extract that electricity. In other words, the electrons. So we're going to actually go ahead and create a voltaic cell. This is a very, very simple thing. It involves two half cells, so two beakers, right? Each one with their own individual solution and a piece of your electrode, in other words, a metal, right? That's your anode or cathode, a copper wire attaching the two of them together, and then a thing called a salt bridge that will complete the circuit. Okay. Give you a few seconds to copy this, and we will go ahead and take a look at the pictures and try to draw this on our own. Anyone have any questions? Okay. So once again, these are just the components of your voltaic cell, and we're going to go ahead and see this visually in the next slide. Okay. So once again, what's here in this beaker is some kind of zinc solution. So zinc positive solution and a zinc bar. It is connected by some kind of wire that will transfer electrons, connected to a copper bar with a copper solution. And then we have the salt bridge in the middle to make sure that the ions flow left and right. Okay, any questions so far? All right, with that said, I want you to imagine this as if you've had this in front of you, okay? The zinc solid, right? What is zinc doing and what is copper doing? Who's receiving the electron? Who's giving the electron?
Copper is receiving and zinc is giving.
Okay, so zinc is the one undergoing oxidation. It's giving away electrons, right? So in order to give away electrons, you have some kind of positive solution here and you have zinc here, right? If I take any single zinc atom, this is a solid. This can be broken up into two parts. Zinc 2 plus aqueous, right? Plus 2 electrons. So I'm literally taking the solid form of this, the mass of this, and I'm breaking it into positive and negatives. So it becomes a positive ion, right? And then the negative electrons. The electrons then leave through the wire. It is gone, okay? So I'm actually putting in more zinc 2 plus. So this solution is increasing in concentration. Does that make sense? The concentration of zinc 2 plus is increasing as this reaction continues forward, because the zinc 2 plus is, well, the zinc is changing into zinc 2 plus, okay? So what we can say about the solid bar itself, the solid bar of zinc here, is that it is actually deteriorating. So we are breaking this solid down into the solution form and into electrons. So we're taking something that's physically there and breaking it down. Does that make sense so far?
Yeah.
Okay. When we get to the other side, the electrons show up through the wire here, and it interacts with the copper 2+. So this is going to join together. This 2 electrons are going to join with the copper 2+. It is going to form solid copper. Okay. So this bar is actually going to get larger. This is actually going to have more solid copper forming on top of it. This solution concentration is going to decrease. Does that make sense so far?
Professor, why
Yes?
do the electrons leave the zinc?
So if we were to compare two metals, right? One of them happens to be, when we compare any two metals, one of them has a stronger pull on electrons. So it will pull the electrons towards it, or it will have a habit of giving away electrons, while the other one has a habit of taking electrons or giving away.
Yeah.
So we'll learn more about that in terms of calculations later on. What happens when the zinc, when the copper 2+ runs out? Then this reaction stops. Because you can't really transfer electrons over if there's nothing joining with that electron, right? So if your solution concentration runs out, then you have no way of making that copper bar. Same thing with the other side. If the zinc solid bar runs out, then you have no way of getting more zinc 2+ into your solution. Okay, what is the purpose of the salt bridge? We will talk about that in a little bit, but the purpose of the salt bridge, so just really quickly, I'll go through it here. We will revisit it later. As electrons are transferring to this side, what's happening to the concentration of this solution? If I'm adding negatives to it,
It's becoming negative.
becoming more negative, right? What about the right side? I'm adding more zinc 2+ into the solution, becoming more
Positive.
positive, okay? Really quickly, any reaction, if you are becoming more positive on one side and more negative on the other, how long is this reaction going to go before it says this is too much? Or better yet, let's say this. You go gambling, right? You have your credit card with you. You play the slot machine, you lose some money. At what point do you say to yourself, when you go ahead and play the slot machine, you have lost too much money? Let's say you have really bad luck. You play once, you lose $100. You play again, you lose another $100. How quickly will you stop?
Playing. We stop playing until we go broke.
Well, you don't want to wait until you go broke, right? Because you're already using your credit cards. You're using money you don't have. Okay.
Oh,
Pretty quickly, you want to stop. You do
Yeah.
not want to spend more money than you have, right? You do not want to go into the negatives. Same thing here. They don't want to become more negative than they need to. This doesn't want to become more positive than it needs to. So the salt bridge, if you look carefully at what the salt bridge has, this has a positive cation. This has a negative anion. So when this becomes more positive, SO4 2- joins in so that this positive and this negative cancel each other out. And then on this side, this positive and this negative cancel each other out so that this electron can keep flowing. Does that make sense? Okay. So that is the main purpose of a salt bridge, but we will revisit that at a later slide. Okay, so once again, these are the half reactions that we just mentioned here. What happens to zinc, what happens to the copper, and then my overall cell reaction. So we can actually calculate this overall cell reaction and find out how many electrons are being transferred by doing our balancing equation. This is where we should usually end up, or it's an easier form of our acidic and basic solution balancing.
Professor,
Yes.
well, what's the solution made of? Like the liquid in the jar?
Zinc 2+ and some kind of anion. It could be any anion that's not participating in the reaction, maybe even some SO4 2-. Okay, this could also be SO4 2-.
Okay.
So it doesn't usually specify. The part that you care about is this and this. You use the metal and its positive ion. That's what we care about, because the anion usually doesn't contribute to anything. It's just either present, taking up space, and just exists.
Got it.
Okay. For those of you that took high school chemistry, in your old school reference table, I believe they still have the 2011 edition. So the 2011 chemistry reference table, there is a section called Table J. That is your activity series. So we're going to learn, not by looking at the activity series, we're going to learn actual calculations on why one will give electrons and the other one will receive electrons. So why something is more reactive than the other. But on table J, there is the activity series. They list zinc and copper and other metals in there. Okay. All right, so let's talk about the operation of a voltaic cell. Okay, we know that the oxidation occurs at the anode, so this is where it is going to go ahead and lose that electron. Okay, over time, we know that the mass is going to decrease. So the actual piece of the zinc is going to start to break down. Okay, the zinc solution is going to increase. And then on the other side, the copper bar is going to increase in its mass. So we're going to get more solid copper. And in the process, we're also going to start to use up some of that copper solution that is there. Okay. Any questions about this? It's pretty much everything we just talked about before. Okay. So to give you a visual, that copper bar is starting to form more copper around it, while the zinc bar is starting to break it down. And so we can actually change the mass and the concentration all at the same time through this reaction. Okay, the anode is also known as the negative electrode in a voltaic cell, and then the cathode is known as the positive electrode. When we go ahead and look at an electrolytic cell, so in other words, a reverse scenario where it's a non-spontaneous reaction, these signs will flip. So it still has anode with oxidation and then cathode with reduction, but the positive and negative signs flip. Okay, any questions? All right. So once again, purpose of the salt bridge, a couple of statements here. It will complete your electrical circuit. It will allow ions to flow freely between both half cells. Remember, as zinc is giving away its electrons, the solution is getting more positive. The other solution is getting more negative. If you try adding more positives to a solution that's already positive, it's going to say it doesn't want that. Remember, opposites attract, same charges repel. So if something's already negative and you try adding more negative to it, it will say, I don't want that. So the way to combat that and solve the solution is to take any kind of negative anion or cation and add it into the solution to balance it out. To make sure both sides stay neutral so that the electrons can keep flowing and you can keep extracting it and using it. One other thing I want to bring up, that when we looked at our electrochemical cells, all of these pictures right here, okay? This is essentially a fancy way of saying a battery. So if you go ahead and look at any AA battery, AAA battery, any kind of battery that you have, it has some kind of electrochemical cell in it. So this is inside of your battery. All of this stuff that you see here, but just on a smaller scale. Okay. So we can also draw this just by looking at the picture here. You can see what is generally happening. We assume that this is my salt bridge, okay? You should not be tasting batteries. That's my only advice. That's a life advice. So don't know how you would know it tastes weird, but should not be tasting batteries. Okay. So once again, in this solution here, this salt bridge happens to have zinc and sulfate in it, okay? So the zinc 2 plus, the cations, is going to the other side to go with the electrons on this side so that this stays neutral. And then the SO4 minus goes to the other side over here so that it stays neutral as well. So the negatives are going to go with the positives. Okay. Any questions? All right. So we have additional things such as the active and inactive electrodes. So active electrodes are the ones that you saw before. They participated in the reaction. So a solid zinc bar or a solid copper bar. So those will participate in the reaction. Okay. We also have inactive electrodes where they do not participate in the reaction itself, but they serve as a conduit or function to transfer the electrons. Things that they tend to use are platinum and graphite. And once again, these are unreactive. They will not react with our reaction, but they serve as things that can go ahead and help us transfer the electrons. So an example here, if I look at the copper bar here. This is a graphite bar. This is actually forming I2 in the process. And then this is going to eventually, well, this solution is a little more complicated. It's not the same as your normal one here. Okay. So it doesn't really involve two metals as much. This involves an anion in the process and then a metal. So MnO4 here functions as an anion. So we're looking at this in terms of anions instead of cations. But once again, you can use graphite and platinum, which will not react, as your inactive electrodes. So they serve as the kind of like the metal rods in these reactions, or the metal bars, or the substitutes for it. Okay, any questions? All right. So the next thing I want to bring up is a thing called the line notation. So we have 3 lines here, a single line, a double line, and then a single line. The single line refers to a separation between phases. The double line refers to a physical separation, also known as your salt bridge. So looking at this picture right here, what this is essentially telling me is that in my equation, it goes from zinc to zinc 2+, and then copper 2+ to copper solid. So it's also telling me that on the left side here, this is my anode, and it's the one undergoing oxidation. Okay, on the right side here, this is my cathode, and is the one undergoing reduction. Okay, and based on just the picture here, I can draw everything that I need. I know that I have 2 jars here, right? I have a zinc bar, and I have a zinc solution. Okay, that is connected to a wire to this side. This is a copper solution. I have a salt bridge here. That's what the double line separation is. And this is telling me that the zinc is changing to zinc 2+. So I'm making more of this zinc 2+. Let me redraw this so you can see it a little more clearly. So zinc 2+ is here, and you have a zinc bar, okay? The zinc is changing into zinc 2+. So the zinc bar is changing to zinc 2+. The electrons are leaving in the process, and it's going to the other side. And on this side right here, based on what I see is I have a Cu2+. This is joining with the electrons that are coming in, and the 2 of these are joining together to make my copper bar. Does this make sense so far? Once again, the line notation is a simple way of essentially, instead of drawing everything, it's kind of telling all the information we need, both in the equation and in the picture. Okay. So this is an example with an inactive electrode. What this is essentially telling me is that I have this in my solution on the left. Okay, I have I2 on the left here, and then I have an I2 solid, okay, in my solution. And in the process, I have a graphite bar, so this is carbon, right? Just change that color so you can see it. And then this is the one sending electrons out. This is the one undergoing oxidation, so does the anode. Any questions? Now, if it happens to be in the same exact phase, you simply separate it by a comma. So they're all in that solution on the right side. But once again, the inactive electrode is one that's a little more complex. You just need to know what could be an inactive electrode. No, graphite will not break down at all. What's happening here is you have some I2. This I2 is breaking down into that. This is just serving as the thing that you use to transfer things, transfer the electrons. Okay, does that answer your question? I'll take that as a yes then. Okay, so what I want you to do is I want you to go ahead and using the information that you see here, I want you to go ahead and give me the full balance equation, okay? Give me a drawing and give me a line notation of this electrochemical cell based on the information that you see here. I'll give you a little bit of time to work on that, and then we will go over it. Okay, really quickly, is anyone having trouble starting this? All right, how many of you just need more time to finish? All right, give you about another minute. Okay, so let's talk about this. If we pay attention to right here, these are connected with their anions. So NO3 is my anion. And you can tell by this is usually -1, okay? So chromium here has a 3+ charge, as you can see from the 3 right here. Silver here has a +1 charge, okay? So with that information, I know that I need to add 3 electrons for this chromium, and I need to add 1 electron for the silver. So if I'm going to go ahead and balance this equation, I know I need to change this number to a 3 so that the number of electrons are equal to the number of electrons on both sides. Okay, so this is just a setup for these two right here. So there should be chromium 3+ plus 3 electrons, 3 Ag plus 1s plus 3 electrons. Some combination of these two things. Any questions so far? All right. With that said, if we read the rest of this, it indicates that the chromium electrode is negative relative to the Ag electrode. So my Ag electrode is considered the positive one. My chromium is considered the negative one. With that said, right, what does that tell me about the anode and the cathode? Which one of these is my anode? Which one is my cathode? Cr is my anode. This is my cathode. Okay. And with that said, what is silver undergoing? Reduction or oxidation?
Is it undergoing oxidation?
It's actually undergoing reduction. Okay. When you see cathode, right, you can see red, reduction. So you can remember this as, if you wanted to, red cat, and then anox. Okay. So if the anode is the one that's negative, that means this is undergoing oxidation. All right. Any questions up to this part? This is just our setup so far. Okay. I'm going to go ahead and clear the screen real quick. If it is undergoing reduction, where should the electrons be? Left side or right side?
Would it be on the right side?
It would be on the, I'm sorry. If we're undergoing oxidation, it should be on the right side. If we're undergoing reduction, it should be on the left side. Okay. So once again, oxidation should have some kind of metal plus some kind of metal in the solid form changes into metal with a positive charge plus electrons. Reduction is where we go ahead and have that some kind of metal that is a positive charge plus the electrons. We're adding it together and it is forming a neutral metal. So these are our two equations that we should look at. Okay. And we're going to go ahead and indicate which one is which by organizing it. And we know that since we said that silver is negative, chromium is negative relative to Ag, right? And that means this is going to be the anode, which also means that this is where oxidation happens. So oxidation is involved with chromium, and this one involves silver. Okay. Any questions so far? Now, once again, with that said, chromium here is just simply chromium solid changes into chromium 3 plus 3 electrons. And then for the other one, it is silver solid. Oh, sorry, silver positive. And remember, we said that this was 3 of them, right? Because we need 3 electrons here. Changes into 3 silver. Oh, sorry, I misclicked. Okay. I'm not going to draw all that again. I'm just going to show you the answers in the next slide. It makes it a little bit easier. Okay. So same thing as I just mentioned. This is your anode. It undergoes the same thing here, changes into 3 plus and 3 minus. And then reduction is the one where you added the positives to each other. Now you want to make sure that you balance this. So this needs to have a 3 here, this needs to have a 3, and this needs to have a 3. So when I look at my overall balanced equation, I need to make sure that this has a 3 on it, this has a 3 on it. These are the things that are missing.
So
Any
Professor-
questions? Yes.
So I just have a quick question. So basically, all it is in terms of the electrons is oxidation, or sorry, reduction is basically the opposite of what it is, where instead of taking it off of the electron and putting it in the products, we add it onto the into the reactants then.
Yes. Reduction is you're taking this thing and you're adding the electron to it. Then you're making that.
So then why is it called reduction?
Because
wouldn't-
the charge goes from positive to 0.
Oh, because it's talking about the charge. Oh, okay, that makes a lot more sense. All right, thank you.
Okay, remember we're adding electrons. Electrons are negative. So you are reducing the oxidation number. Okay. All right, with that
Yep,
said,
thank you.
we can also draw the drawing. We know that's chromium 3 plus in the solution. And since this is the one that is anode, remember the anode is always the one drawn usually on the left side. I would say 99% of the time, they should draw the anode on the left side in the line notation. In the pictures that they have here, sometimes they don't draw it that way. Sometimes they'll really be messed up. They'll draw it on the other side, and then they indicate the arrow goes this way. But as long as you know that the electron is leaving, that is the anode. The electron leaves the anode and goes towards the cathode. Any questions? Okay. So let's go ahead and continue. Once again, I drew the balance equation at the bottom. You want to make sure that it says 3 in the front of these because you want to make sure the same number of electrons are being transferred on both sides. Okay. So let's talk a little bit about the electrical potential. Okay, so it's also known as E cell, and then we have the standard reduction potential as well. So between zinc and copper, zinc is a stronger reducing agent. So what does that mean when you're a reducing agent?
You make the other element go through oxidation.
Yeah, not quite. You are a reducing agent. So you don't make the other thing undergo the oxidation. You undergo oxidation. What do you cause the other thing to undergo? Reduction. You cause something else to undergo reduction. Okay, so zinc is a stronger reducing agent. It will cause copper to undergo reduction. It itself will undergo oxidation. So we'll learn about whether something is a stronger reducing agent or a weaker reducing agent, or in other words, has a stronger reduction potential. Okay. So once again, we will learn about the electrical potential in a little bit, but for the time being, know that zinc is stronger in that sense. That is why this is the one undergoing oxidation and this is the one undergoing reduction. Okay, any questions? All right. So let's learn a little bit about cell potential. Cell potential can be referred to as E cell. Okay, it is actually related to delta G. So in order for something to be spontaneous, we want E cell to be positive. Okay, once again, we want E cell to be positive. Remember, when we wanted something to be spontaneous, we wanted delta G to be negative. So these are related in that sense. When delta G is negative, E cell is positive. Okay. Any questions before we move forward? You don't need to know so much about the voltages. This is not as important. This is just to give you an idea of what voltages are based on the different objects that you have. So we can measure things based on the standard cell potential, also referred to as E cell. So we have two things we're going to learn about: standard cell potential and standard reduction potential. We'll learn about standard reduction potential in a bit, but standard cell potential, sometimes referred to as just cell potential, is your E cell. This also helps us kind of measure the voltage. Okay, so in order to figure out what our value of E cell is, it is always going to be this setup right here. It is always going to be the cathode minus the anode. Okay, what did we say the cathode was? Was it the more positive one or the more negative one?
The more positive one.
The more positive one. So the best way to do this, and this is just to make sure that you don't get confused, anytime you have two numbers, given any two numbers, when we're talking about voltages, right? Put the more positive one on the left, subtracted by the more negative one. Simple as that. That will always give you some E cell here that is positive, and that will make this reaction spontaneous. Does this make sense so far? Remember, we want E cell to be positive. So in order to be a spontaneous reaction, I put the more positive one minus the lower value. Okay. The more positive goes on the left, that is your cathode. The more negative goes into your anode spot. And no matter what I do to whatever reaction I'm looking at, I can double the amount of the reaction, triple the amount of reaction, change the heat, whatever. It is always this value. This is independent on how many moles I have, independent on anything else. Even if I flip some signs here and there. Keep it as the most positive minus the most negative. And you will always have the right answer. Okay. So I'm going to refer to a thing called the standard hydrogen electrode. Hydrogen is my reference point. So everything is revolved around hydrogen. All of the numbers that you see here, you're going to see a bunch of these E numbers with voltages, right? These are all in relationship to hydrogen. So if I take hydrogen and hydrogen itself, so I'm comparing hydrogen plus hydrogen, the difference between these two numbers is that, which is 0. Okay? If I change this to like iron, for example, the difference between hydrogen and iron should be some value. That is how we determine these numbers. Okay? Hydrogen is my reference point. Any questions? All right. With that said, okay, I will do this problem with you so that this way so you have a better understanding. This is the value of zinc. This is the standard reduction potential of zinc, okay? This is the standard cell potential of the two things joined together. I have bromine and zinc joined together. So I'm putting bromine and zinc together, okay? Zinc here has a negative number. I want you to find the charge of bromine, okay? The way that this is set up, I always have my E cell here. If I want this to be a positive value, it happens to be 1.83, right? This is always going to be equal to whatever the cathode is minus the anode. Also, in other words, this is the reduction and this is the oxidation. And we said that this one is going to be the more positive value minus the more negative value. Does this make sense so far? I'll take your silence as a yes. So if I look up here, who is undergoing reduction? Who is undergoing oxidation? What is zinc doing? By looking at this, what is happening to my zinc? It's undergoing oxidation, right? So this is going to be undergoing oxidation. That also means that this is my anode, and also means that this is my negative one, okay? Bromine here is undergoing reduction, okay? So if bromine is undergoing reduction, this is my cathode, and this is also my positive value, okay? Or should have a more positive value when I calculate this. So once again, my E cell, which is 1.83, is equal to whatever my value of bromine is okay? Minus this value right here for zinc. And I know this value, so I can plug that in. It is equal to negative 0.76. So let's go ahead and replace this. I'm going to do a little bit of algebra here, okay? So I'm looking for that, and this is minus 0.76. Any questions? Okay, with that said, we can plug it in and get our answer right here. It comes out to 1.07. Okay, so 1.07 is my value of bromine. This is the standard reduction potential of bromine. Another way we can look at this, just so you can compare this one and this one, right? These are known as your standard reduction potentials. They are for individual elements, and they are always based on the reference point of hydrogen. Which one of these is a bigger number? Not a trick question.
The voltage of E and for bromine.
Okay, so the bromine standard reduction potential is a bigger number, right? What that essentially means is that if I had to compare bromine and zinc, who is more likely to undergo reduction? And the answer is going to be bromine. Does that make sense? Once again, if it has a higher number, this is more likely to undergo reduction. So if this is the one that undergoes reduction, this is where the cathode happens. This is the one that will receive the electron. This is the one that will give the electron. Okay? You can almost think of it like it's larger, the number is larger, this is the bully. This is the one that collects the lunch money from the other one. Okay, any questions?
No, that makes sense. But the formula is basically can you just put that back up on the screen real quick if it was shown to us? Because I
This
just
one
want
or the equation?
just the equation for E. Oh, okay. I
This
just wanted to want to make sure that I had it written down correct, which
Okay.
I mixed up cathode and anode.
Okay, you got it now?
Yep. Thank you so much, Professor.
All right. So let's go ahead and compare this information. Once again, the more positive the value is, the more likely it will undergo reduction. In other words, it is acting as an oxidizing agent. It's going to cause the other thing to undergo oxidation. So if you want to remember by lunch money, it's the one causing the other one to give up its electrons. It says, give me your electrons. Okay. The more negative one is the one that will act as the reducing agent. It will be the one that gives away the electrons to the other source. All right. So this is a list of your standard electrode potentials, also known as your standard reduction potentials. Once again, hydrogen is my reference point. So I'm going to give you two things here, and you're going to go ahead and tell me which one is your cathode, which one is your anode. Okay. I'm looking at silver and copper. I'll just circle them for you so you can see it. Which one is going to be my cathode? Which one's going to be my anode? Silver is the cathode, copper is the anode. So when I write this equation in, right, I am going to essentially calculate my E cell as 0.80 minus 0.34, okay? And it's always going to give me a positive value. Does that make sense so far? When I write my equation out, right, when I write this equation out, this would be written as Ag plus electron changes into Ag solid, right? And then this equation is flipped because this equation is now undergoing oxidation. The way it's written is undergoing a reduction. I'm going to flip it because this is the one undergoing oxidation now. So this is going to become Cu solid changes into Cu2 plus 2 electrons. So when I put the two equations together, I have Ag plus an electron plus Cu solid, and then changes into Cu2 plus 2 electrons plus Ag solid. With that said, I also need to make sure that it is balanced. So I put a 2 here, a 2 here, a 2 here. I cancel out the electrons, so it becomes 2Ag plus Cu solid changes into Cu2 plus Ag solid. Any questions? I'm hoping you got all of that. Okay. Does anyone else need time to take a picture of this, copy it down, put it to memory, whatever you
Yeah,
need to do with
Professor,
this?
I'm just going to retake the picture because it didn't come out good.
Okay.
1
There's
second.
also a screenshot function on your computer. If you're on a computer, I believe it is Control Alt and print screen. You can go ahead and copy paste it and drop that into a Word document.
Thank you.
You should be given these values, yes. Or you should be able to be given enough information to assume certain values. So they may not give you the hydrogen value. They may tell you this is hydrogen. You should assume that the hydrogen is always going to be 0 voltage. Okay. So once again, when we're trying to figure out whether this is going to be a spontaneous reaction or not, we always go ahead and calculate our E cell. The standard reduction potential that has a higher number is the one that undergoes reduction, also known as your cathode. Okay, so you don't need to know the details about this. It's pretty much the same thing that we just spoke about. So I'm going to give you this information right here. You are given tin and silver. Okay. Write this in a spontaneous reaction, or write this in a form that where it will be a spontaneous reaction. What's on the cathode side? What's on the anode side? I'll give you about a minute to do this, and then we'll go through it. Should be quick. And you can also determine the value of my E cell based on this. And make sure the equation is balanced. Okay. Who is able to determine which one is the cathode, which one is the anode? Okay, silver is my cathode, tin is my anode. What does my overall E cell value come out to? 0.94 is correct. Okay, so let's go through this. Okay. Number one thing you want to do is make sure that you reverse the sign for this one. So that's not the sign, you change the entire equation. So the setup looks like this. Okay, because this is the one undergoing oxidation. So it's the one that actually going to be giving away the electrons. So you want this written in the right way. If you notice, what did I do to the E value here? Nothing, right? I keep this the same. I do not touch this, even though I changed the sign. This is known as my standard reduction potential. So how likely it is undergoing reduction. I do not want to change this because if I change it, it becomes my standard oxidizing potential. I don't need this information. I want standard reduction potential, okay? Because I'm comparing it between these two. All right, with that said, it's also going to help us when we calculate our E cell. So I plug it in. I can go ahead and calculate my E cell. It comes out to 0.94 volts. We also want to make sure that we balance the equation. So we need two of these. What happens to this value here when I doubled the silver?
The value doubles?
Did it double?
No.
It stayed the same, right?
Yeah.
So even though I flipped this sign, this stayed the same. Even though I doubled this concentration, this stayed the same. So my biggest hint for you and my biggest advice, don't mess with the standard reduction potentials. Keep them the same value. Do not change them. Do not flip them. Do not do anything with them. Okay, take them as is, put them where they belong, subtract them, get your answer. Any questions? Okay, with that said, I can now go ahead and say that it is 0.8 minus negative 0.14 gives me positive 0.94. That is my answer. And my equation is also balanced here. This was flipped over to the other side. Electrons are canceled out. This is on your left. This is on your right. Any questions up to this part? Okay. With that said, I want you to, if you can, use the space that you have wherever you plan on writing it. Draw me the line notation of what you see here. Once again, draw me the line notation of what you see here. Okay, does anyone else need more time to draw this? So your line notation should look like this. You have your SN and this is your solid, okay? That's your electrode. And on this side, you should have your AG. I don't need the 2, so you don't need to include the 2 here. This is your solid. Let me redraw that. Okay, it's your solid here. In the middle here, this is SN2 plus, and over here, this is AG plus. So if I were to visually draw this picture, it would look like I have this on the left side. I have the SN solid, right? And then SN2 plus in my solution here. Okay. And then on my right side, I have the solid bar of AG. That's also indicating that the electrodes are out here. Okay. And then I have the AG plus solution. I have a wire that connects the two of them. And then I have a salt bridge that is in the middle. And you have essentially drawn your battery, also known as your electrochemical cell. Any questions? Okay. Let's continue now. So I want you to try out this problem here, okay? So same concept. I want you to find the overall balance equation, show me the line notation, calculate everything, determine which one is what my E cell is, figure out which one's my positive, which is my negative, and then draw me a picture, okay? And also the line notation. Give you about 2 minutes to do it.
Professor,
Yes.
is it the oxidizing agent minus the reduction agent, or is it like
So the best way to remember this is your cathode minus your anode.
okay?
Okay.
Yeah,
So I don't want you to start getting confused with the oxidation agents because I never like to refer to things as agents. Okay. But you know what those mean. They cause the other thing to undergo oxidation and
Mhm.
reduction. Okay.
Okay.
So if you really want to get specific, this is going to be your reduction and this is going to be your oxidation.
got
Okay.
it.
And if we're referring to agents, that would mean that this is the oxidizing agent. So you see how this is like 3 times removed. It's more complicated. It's easier just to refer to it as cathode, anode, or reduction oxidation.
Got it.
Okay.
Yeah.
All right. With that said, between aluminum and magnesium, which one of these is my more positive value? Just that. Which one is more positive? Okay, this is the more positive value, right? That means this is the cathode, which also, again, means that this is the reduction and onwards and onwards, okay? So when I go ahead and draw this, okay, before I do any of this, let's first just separate this. This is my cathode, and the bottom is my anode. That's where I undergo oxidation, okay? So if we look up here, it makes sense. This is undergoing reduction, right? Fits perfectly. This is undergoing oxidation. So it fits perfectly in our picture here. All right. With that said, let's calculate E cell, just the value of E cell. This is your negative 1.66 minus negative 2.37, which gives you positive 0.71. And it shows it's a spontaneous reaction because this is a positive value. Okay. Can everyone see that? Any questions? All right. I'm going to go ahead and clear the screen real quick. Ashley, to answer your question, you almost have it all correct. Almost, okay? With your drawing there, when I draw my line notation, and this is a very important one, what should always be on the very left side, this side right here? The anode. Okay, so this is the one undergoing oxidation. Now we know that this is our anode. This is the one undergoing oxidation, okay? So we start with the metal solid here, okay? And it is changing into the ion form because this is undergoing oxidation. So that is why it should look like this. And then on the other side, this is telling me that this is my cathode is undergoing reduction. So this is the one receiving those electrons and changing into a solid. Okay. Any questions about this here? And if you're also confused, when you go ahead and write your balanced equation, right? This is on the same side here. And then you have the separation in the middle, right? Oh, I'm sorry, I drew that wrong. Okay, so this is on the same side on this one. This is on the same side over here, okay? And then this is over here, and then this is over here. So if aluminum is on the right side, aluminum solid is on the right side, it should aluminum solid be on the right side. This is on the left side, this should be on the left side. Okay? Any questions?
Oh wait, Professor, yeah, I'm sorry. I just wanted to make sure. So then, in this case, if it told you to find the actual value, then we would just do negative 166 plus 237, since the minus the negative cancels out.
Yep. So
Okay,
it's
perfect.
negative minus of a negative just becomes a positive.
Okay, I wanted to make sure I have the setup all correct. Thank you.
Okay. Now with this all said, right? We already found the E cell, we need to balance the equation. So if I look here, there's 3 electrons being transferred, 2 electrons being transferred. So I go ahead and simply multiply this by 2, this by 3. So every one of these should have these numbers in front of it, so that my overall balance equation makes sense. The electrons being transferred is equal to 6 on both sides. Any questions? Now, based on all the information you have here, including the line notation, you could actually draw this if you wanted to. So I can draw this on the left side and this on the right side here. So this is the one undergoing oxidation. So this is essentially your magnesium bar, and then your magnesium solution, okay? Here you have your aluminum bar and then your aluminum solution. And the electrons are being transferred in this direction. And then you also have a salt bridge. For the salt bridge, we can come up with any solution we want to put in there. I can put it as KCl, KNO3, something that will have the potassium going this way to help it, and then the NO3 going this way to assist. So make sure that things stay balanced and neutral. Any questions? Okay. So with that said, we can now relate delta G and E cell. This is the equation to relate the two. So we spoke about it earlier. E cell, when it's positive, is considered spontaneous. Delta G, when it is negative, it is considered to be spontaneous as well. So this is how the two of these are related based on this equation right here. The N stands for number of electrons being transferred. F is a constant, is known as Faraday's constant. It is this number right here. It is joules per voltages over moles per electron. Times moles per electron. Or moles and electrons. Yeah, per electron. That's what the negative one means, sorry. Or sometimes they refer to it as just electrons. Okay. Any questions about this setup here? All right. So we can actually go ahead and take all of the equations that we learned from delta G and remake those equations. Okay. So we can get these two new equations down here. So we can relate E cell now to K. Does anybody remember the equation for delta G with K? Remember, delta G at standard state is equal to negative RT ln K. So we're essentially taking what we learned here, and now we're going to relate E cell to K. Okay, just a quick check. Does anyone want me to show them algebraically how we got to this equation here? Or you can figure it out by looking at these two equations.
I'm pretty sure it's somewhat self-explanatory.
Okay.
Oh,
Just making sure.
actually, just one question. The ln K, that comes from the delta G, no?
Yes.
Okay, perfect. Thank you.
So if you look at the equation down here, all I really did was I changed this value by plugging this in. This is negative NF E cell, right? And I want to get E cell by itself, so I divide this side by negative NF, okay? Now with that said, I divide this side by negative NF. The negatives are removed, so this just becomes E cell is equal to RT ln K over NF.
Wait, but Professor, it's not over it's not over NF in the equation. Is there any reason for that, or is that just because it wasn't gonna fit like on the equation?
You can put it not over the ln because ln is a function, so it's ln of K. So you wouldn't
Okay.
include it with that, you include it at the bottom here.
Okay,
Okay, I
thank
just
you.
drew it there because that's the quickest way to show you.
Okay, thank
Okay.
you.
And then the equation on the right side, this is related to the Nernst equation, so it plays a part as well. So really quickly, I want you to look at this equation here, okay? R is a constant. N is a number of electrons. That's not a constant. F is a constant. I have two of these as constants. Ln is part of a constant, okay? If I set the temperature to be 298 Kelvin, also known as 25 degrees Celsius, right, room temperature, then this is also considered a constant. So these four constants related to our K here can be rewritten as this number right here, 0.0592, and then change that to a log of K, okay? So this is essentially, if it's 25 degrees Celsius, I can remove all of these constants here and change them all into this number log of K. Okay? This is just something to keep in mind of. If you ever end up with a scenario where the temperature is 298 Kelvin, you know, it's 25 degrees Celsius, you don't have to look at this equation. You can just look at this equation. Gives you the numbers you need. All you got to do is look at the number of electrons, and then that will help you figure out your K value, or if you are trying to solve for your E cell, depending on which one you're looking at. Okay. With that said, you can relate all three of these together now. Your equilibrium constant, your E cell, and your delta G. So once again, yes, we go back to equilibrium. So we are constantly going back to equilibrium. So this is why I mentioned every single one of the chapters you've learned from chapter 17 and onwards involves some form of equilibrium. Okay, does anyone need time to copy this down? It can also be found in your textbook. Okay, let's continue. All right, so now we're going to go ahead and combine our previous equation. So remember, your delta G is equal to your delta G at standard state plus RT ln Q. Okay, so remember our old equation here. We're going to go ahead and plug in my negative NF E cell in the process. So we go ahead and put that in for every single one of these. And this one we're going to call it at standard state. Okay. So the best way I can do this is now I'm going to go ahead and divide all of these by negative NF. So just to make sure that you don't get confused, it doesn't cover the LNQ. So this part is gone right here. This part is gone. And this becomes negative NF on this side. So our new equation is going to be E cell is equal to E cell at standard state. And since this was a positive before, we're going to go ahead and change it to a negative because we have a negative here. So it is now negative RT over NF ln Q. That is how we got to this equation here. Any questions? No questions? Okay. Now let's go under another assumption. 25 degrees Celsius, right? So this becomes 25 degrees Celsius, also known as 298 Kelvin. This is a constant, so I have constant, 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 and then I have this as a constant. What can I change all of this to? Just like what we did before with our K example.
The number 0.0592.
Yep. So we get E cell is equal to E cell at standard state minus 0.0592 over N log of Q. Okay. So we can essentially remove all of these unnecessary constants and change it into this right here. And again, this only applies at 25 degrees Celsius. Now, with that said, this is the equation you should be getting at the very bottom. And this is also known as the Nernst equation. Question? Okay. So once we get to this equation down here, we can actually relate things based off of this alone. Okay. When Q is less than 1, the reaction will move forward this way. In other words, my E cell is more positive than my E cell at standard state. Okay. If Q is equal to 1, that means it is at standard state. So E cell is equal to E cell at standard state. When Q is greater than 1, then this is essentially telling me that this is more positive and this is more negative in comparison to each other. Okay. Any questions? Anyone need time to copy down this equation? All right. So before we jump into this equation, just to make sure that we have enough time to go through everything, I do want to put a disclaimer out on this question here, okay? So I've had many talks with the textbook company about this. Normally, whenever you see something that is in the form of pressure, you want to change this to make sure that they are all in the form of concentration, just like when we learned about our relationship between Kp and Kc, okay? So what they would have done was if we took our BV equals nRT equation, we go ahead and move the N and the V into the same side. So this would essentially give me the concentration. I would do all that just to make sure I get the concentration of this value. Problem with this is in your textbooks, they keep this as is. So they don't change this value. This stays as this. This is also essentially written as that. And the reason why they justified it is that the change is so negligible, it is insignificant. Okay, so we'll go with their assumption. So what you're going to see in my calculation on the screen here is slightly different than the one found in your textbook. Okay, just so you know that. This is my disclaimer for you. All right, any questions?
So you want us to do this question as it's done in the book or as what?
You can follow the one that's in the book. More than likely, you're never going to see a question like this in detail. So they
Okay,
wouldn't be asking you to do all of that, but this is to challenge you to make sure you understand how to go all the way back in the information from Chem 1, all the way back into figuring out equilibrium, all the way back into just solving molarity in general. Okay, so
Got
it goes
it.
all the way back to our Chem 2 stuff, and then it also goes all the way back to Chem 1 stuff. Okay.
okay, okay, thank
But
you.
once again, the textbook, they changed it up over the editions. They used to have this exact same format, the format that we did here. This was like 5 years ago. Then they changed it 4 years ago. And then since then, it's been a constant conversation back and forth. But we'll take their word for it. They said it's insignificant, doesn't really matter. We'll go with their definition in the textbook. So in case you see it, there's a difference. It's okay. Okay. All right. So I'll give you some time. Try to see if you can figure this out. You are solving for the E cell given all the information that you have here. Okay. You will need to make at least one assumption in the process that is related to your H2. Other than that, everything else is pretty straightforward. Any questions? Okay. I'll give you about 3 minutes to try to answer this. Then we'll go through the entire problem. And then after that, we will do the polls. Okay. Is anyone confused about this problem? All right. So let's go through this real quick. We're calculating the E cell, so we have to use the entire equation. But in order to do that, we also need to find the value of Q. So if I go ahead and start this, I'm going to go ahead and just simply find my E cell value in general at standard state. It is 0, which happens to be the reference cell, because we mentioned hydrogen. So 0 minus negative 0.76 will give me positive 0.76. This is my E cell at standard state. Okay. Any questions so far? All right. With that said, I also want to go ahead and find the concentration of H2. So this is the part where there's a little controversial depending on what they mentioned in the book, right? So for us, we go ahead and use the PV equals nRT, rearrange the equation, plug it in, and solve for the concentration of my H2. The way that they have it in the book is they kept this as 0.30. So the number is a little bit off compared to what I have here, okay? And it'll show up later on when we calculate our Q value. It's a very minor difference, but it's still a difference nonetheless, okay? With that said, I now have my H2 value here. So I have my concentration. I know my other values are, right? I simply plug them in. I get this as my Q value. So 1.9 times 10 to the negative 5. Any questions up to this step here? All right. With that said, I can plug it into my equation. We are under the assumption that this is 25 degrees Celsius. I can use the Nernst equation, makes things very easy. This is the log of the value, and I know this is 2 electrons being transferred. Okay, with that said, I plug everything in. We are simply calculating E cell. It comes out to 0.90 voltages. I believe the one in the textbook gives you something like 0.8 voltages because the number is difference is because they accounted the Q to be slightly different. Okay, but everything else works the exact same way. So it's just that debate about the value of Q because the value of your H2 concentration. That's where this came from. So if you take a look in your textbook at 21.7, you will see that there's that slight difference. Someone had a question?
So Professor, the Q is the concentration of H2?
No, the Q is not the concentration of H2. The difference is the concentration of H2 will vary depending on what the textbook says and what you see on the slides here. And that will change your value of Q, which will change your value of the voltages.
How did you find out Q again?
So Q is equal to these concentrations here. Okay, this is your products over reactants. The only one that was different was this one right here. So in the textbook, they would have this as 0.3. Okay, which would change whatever this is, which would change your value of your E cell. That make
So
sense?
was it like a mistake in the textbook or?
So if you want to go into it, 5 years ago, they had this exact format here. They actually did this. And then 4 years ago, they decided to say that this can just stay as 0.3. They decided not to do that. And it didn't make sense why they decided not to do that. And for the last 4 years, I've been emailing the publisher. We've been talking about it. And then they said that based on their other textbooks and other instructions that they have, they said there's no point of changing. We're just going to keep it the same. They decided to count pressure and concentration as the same. Now, I disagree with that. So that is why I keep it the way here. Again, a question like this will not show up on your quiz. If it does, you have one less thing to worry about. That's going to be given to you as just concentration. So you don't have to worry about changing between ATM and concentration.
Okay, got it.
Okay?
Yeah.
All right. So with that said, we plug everything in, you get 0.90 voltages. Again, in the textbook, it's going to have a different number than what you see here. Okay? Now, we're going to come back to this stuff right here, and we will finish that next week. Just some things I want to bring up before you suddenly leave. I saw someone just left. So really quickly, there will be a poll, so I'll send that out in a second, right? Those in the Friday class, you are taking your chapter 20 quiz this week. And then those in the Tuesday class, you're taking your chapter 20 quiz next week on Tuesday. Okay, just want to make sure that you get that information. In addition to that, I believe that Queens College themselves have opened up their evaluations. So go ahead and fill those out for me. They're open until I believe December 13. Sometimes they extend it afterwards. For those evaluations, the only people who see those comments is me, and it'll be way after the semester ends. Okay, so I highly recommend being as honest as you can be. Even if it's a brutal comment, I will take it. Be as honest as you can be. Okay, it doesn't trace back to you. No one will see that. Okay, any questions so far?
Professor, I couldn't hear you for a moment. You just kind of went.
Okay. So once again, if you're in the Friday class, you are taking the quiz this Friday. If you're in the Tuesday class, you're taking the chapter 20 quiz next Tuesday. Okay. Also, with that said, QC evaluations are up. The only person who sees the comments is me way later. So not even right now. They probably won't be available until the end of December. Okay. So be as brutally honest as you can be with those comments. Okay. I will go ahead and find out where the evaluation links are. I believe they mentioned it. I don't know if they uploaded it yet. Okay. Other than that, I'm going to go ahead and open up the polls. For those who are co-hosts, you can go ahead and stop recording if you were recording. I'm going to go ahead and remove the co-host privileges.
Professor, I have a question.
Yeah, go ahead.
They asked in the comments too. They're asking when the final is gonna be. If you said already the date.
So I'm going to assume it's going to be the 14th, but again, I don't know if they're counting that as a study day or not. So I will find out from the department, and as soon as I find out, I will let you know.
Okay, thank you so much.
Okay. I don't decide that whether it's going to be the 14th or 21st. That is something the department will decide. Whichever day is our normal Tuesday class and not a reading day, that is the day we do the final. Okay. Any other questions before we start the poll? All right. Okay, so you have about 5 minutes to finish the poll. Well, it's only 4 questions, so 4 minutes should be enough time. Okay, and if you have any other questions for the time being, you can message me here. Other than that, we will begin office hours afterwards.